Okay, so we are in the process of defining the Lebesgue integral. So when we had phi, so x s mu is a measure space, and phi greater or equal to 0, simple function. So phi equals sigma I equals 1 to n alpha I chi of ai, and then whatever these sets may be, we have that integral of over x of the function phi with respect to the measure mu is given by sigma I equals 1 to n alpha I mu of ai. Okay, and in case of e contained in x, then we said integral over e phi d mu is nothing but integral over x phi of chi of e, phi into chi of e d mu. Okay, so we now continue with this. So now we are going to do non-negative functions. So x s mu measure space, f non-negative extended real valued function, measurable function, sorry, on x. Then the Lebesgue integral of f over x with respect to the measure mu is defined by integral f d mu over x equals sup of integral phi d mu over x, 0 less than or equal to phi less than or equal to f, and phi simple. And if e is contained in x, measurable, integral over x e f d mu equals integral over x f into chi e d mu. Okay. So recall that given we proved a very important theorem earlier. If f is a non-negative measurable function, then it is the increasing limit of simple non-negative functions, and therefore this definition makes sense. Now, by the remarks which we made at the end of the last session, it is clear that since if you have two measurable simple functions, one less than the other, then the integrals have the same inequality between them, and therefore by earlier remarks these definitions agree with the ones made earlier for simple functions. So if f is a simple function, then this definition agrees with the previous definition. Okay, so that is obvious from the two remarks which I made at the end of the previous video. So you please go and check that those two will be good. Now, so again remark, integral f d mu over x can be infinite. Okay, so next proposition, very trivial one and immediate from the definitions. So xs mu a measure space, and f non-negative extended real valued measurable function defined on X. A. If G is a non-negative measurable function such that 0 less than equal to G less than equal to F, and E contained in X measurable, then integral G d mu over E is less than or equal to integral over E f d. B. If E and F are measurable subsets of X and E contained in F, then integral over E f d mu is less than or equal to integral over F f d mu. C. If C greater than 0 is a real constant number, E contained in X measurable, then integral Cf d mu over E equals C times integral over E f d. Then D. If E contained in X measurable, F restricted to E equal to 0, then integral over E f d mu equal to 0. And E. If E contained in X measurable and mu E equal to 0, then integral over E f d mu equal to 0. Okay, all these are immediate one-line deductions from the definitions. So proof, exercise. Okay. Next proposition. Excess mu measurable, measure space, F x to R non-negative. So now non-negative measurable function and integral over X f d mu equal to 0. Then f equal to 0 almost everywhere. So if you have a non-negative function whose integral is 0, then the function has to be essentially 0. Okay, so let fn equals set of all x in X such that fx is bigger than 1 by n. I don't have to put a modulus because we are dealing with non-negative functions, and this is true for all n in n. Okay, then set of all x in X such that fx is not equal to 0 is nothing but the union n equals 1 to infinity of fn. Now if you take integral of f d mu, this is given to be 0, but that's greater or equal to integral fn f d mu by one of the properties which we proved earlier, and on f this is bigger than or equal to the constant 1 over 1 by n, so this is bigger than or equal to 1 by n mu of fn. And this implies that mu of Fn equal to 0, and therefore since it's the union of sets of measure 0, so this implies that F equal to 0 almost. Proposition X S mu measure space F from X to R non-negative phi, let me say phi, simple function. Let E belong to S, define nu E equals integral over E phi d mu. Then nu is a measure on S. So the indefinite integral gives you a measure. Okay, so proof. Indefinite integral, because I am saying the integral taken and over arbitrary sets of the sigma algebra. So nu of E is of course greater or equal to 0, and nu of the empty set is obviously 0. So sufficient to check countable additivity. So let E equal to union n equals 1 to infinity Ei, Ei in S, all mutually disjoint. So let phi be given by sigma j equals 1 to k alpha j chi of aj. Okay. So what is nu of E? Nu of E is integral by definition phi d mu, and that's equal to sigma j equals 1 to k alpha j mu of aj intersection E. That's the definition of integral over E. Now E is the disjoint unions of the Ei's, and so therefore this can be written as mu of aj intersection E is sigma j equals 1 to infinity alpha j into sigma of I j equals 1 to k, sorry, I equals 1 to infinity mu of aj intersection Ei. That is just because of the countable additivity of the measure. And now you have one finite sum here and the infinite sum, all non-negative. Anyway, you can easily change the order of the summation. I equals 1 to infinity sigma j equals 1 to k. It's like summing k series at the same time. So alpha j mu of aj intersection Ei, and that's equal to sigma j equals, sorry, I equals 1 to infinity, and this by definition is nothing but the integral over Ej of phi d mu, and it's equal to sigma I equals 1 to infinity mu of Ei. Okay, so that completes the proof. So now we are going to prove an first step of an important property. When you know you have integration, that's a linear operation. If you take sum of functions and integrate, it's the sum of the integrals and so on. But these things have to be proved now with the definition which we have given, and therefore as a first step towards this we have the following result. So excess mu measure space phi psi non-negative simple functions. then integral over x phi plus psi d mu is equal to integral over x phi d mu plus integral over x psi. So you take phi equals sigma I equals 1 to n alpha I chi of ai, and psi equals sigma j equals 1 to m beta j chi of bj, aj disjoint, bj, so ai I equals 1 to n, and bj j equals 1 to m disjoint. We can write in many forms, as I said, and you can always write it in terms of disjoint sets. So now you set eij equals ai intersection bj. Now eij's are disjoint. Outside union over I equals 1 to n union j equals 1 to m eij, phi psi are both 0. Okay, so now integral phi plus psi d mu over eij. So over eij, what do you know about? And also you have phi plus psi can now be written as sigma I equals 1 to n, sigma j equals 1 to m, alpha I plus beta j into chi of eij. So phi plus psi, so now you have again a disjoint thing here, and therefore this is equal to sigma I equals it is only on eij, so you have your alpha I plus beta j times mu of eij. But that's nothing but eij is a subset of ai and a subset of bj, so this can be written as integral over phi d mu of eij plus integral over eij of psi d mu. So now over union of eij's are disjoint. Each of these is a measure. Okay, this is a measure, this is a measure, this is a measure, and therefore you know by countable additivity you can write over the union. So result follows from previous proposition. Since integral phi plus psi d mu over e integral e phi d mu integral e psi d mu define measures and eij are all disjoint. Okay, so therefore by countable additivity the result will follow. Okay, so now we will of course expand this result to a much better result later on. Our next aim will now to look at limits. So one of the drawbacks we saw in the Riemann integral was the limit of a integrable function is not integrable and so on. So those are the things. So we will now try to study something about limits of integrals of sequences of functions, and of course we are still restricted to the case of non-negative functions. Okay, and we'll do that next time.